Let me share the screen. So I think after a week, right? So I guess it would be good to review what we have covered last week, right? Because it's been 7 days over the long weekend. We're likely that the memory is not going to stay that long. So let me go over details somewhat, a little bit about the random variable. And then today the goal is to finish the discrete random variable with a quiz on Thursday. Okay, similar to the quiz we have so far. So just multiple choice, attendance based. But will not be focused on proof, but will be something like the example in the green box. So the green box in the slides will be something, the green box, something are the question style that I'm asking. The black one are the those technical slides are not the goal of the quiz. You also again not to focus in the final, not the final, the test we have. Okay. And just remember the homework is due Friday next week, okay, midnight Friday. And I'll talk a little bit more about the project, I think, next class, because I think many of you just joined, right? Not many, but some of you just joined. So I just give you a little bit more time if you want to form groups or what, but I will talk about that later after in the first day of quiz, and also we talk a little bit about the projects, so on and so forth. But before we start, any question about what we covered last time? If no, then we just review, and then in the meantime, the question you can just feel free to ask. Because the goal today is just to finish the discrete random distribution. Okay, discrete random probability. Okay, so random variable. Okay, can you see the slides and hear me? If that's the case, can you type OK to the chat? Yeah, good. So just to remind you, what is random variable? Random variable is a mapping outcome to num. No, you don't have to focus on the proof. No, the proof is just for you to understand why they're true, right? But after that, you don't really worry. It's just like the math, right? When you learn Pythagoras theorem, a squared plus b squared to the c squared, right? You learn the proof, but after that, then you know the idea. You don't need to reproduce the proof. You're not math class, but for education purpose, we need to learn why they're true, right? But we don't. Sometimes we don't really need to reproduce those kind of things, but you better know, right? Just like swimming, right? Probably you know the steps, right? How to swim, but there's some physics behind. It's good to know how to improve, but when you really swim, we don't really need those kind of things, right? And sometimes we don't actually, I mean, we know how to swim professionally, right? But sometimes just can't, right? But at least it's good to know what's the target we have. Like the math here, sometimes it's good to know why they're true, but you don't need to memorize it, and we are not expecting you to reproduce that, definitely. But as in the quiz, you will see the style that application, right? So that's why the main focus is the application, but you need to know why they're true. That's why in the project, the homework, we will be working on those. In the case where the proof may be needed, maybe just the homework may ask you to do some, might be the proof, but the proof is not focused. So it's never focused for the class, but we cover it because you need to know why this is true, right? Does it make sense? Soon. Did I make myself clear? Okay. So just to repeat, random variable. What's random variable? It's a mapping outcome to number. In other words, it's assigning number to outcomes. Okay. each outcome, we may put a number there. And the reason why we want to focus on number is to reduce the complexity, right? Otherwise, the number of outcomes can be huge, and to describe them will be a big object. But when we collapse them, measure them into a number, that'll be easier, right? Actually, in the real world, a lot of time you give some measurement to the outcome, right? Just give some number to that, right? Just like tossing a head or tail, right? A coin. Then usually we just count number of head, number of tail, right? And that means if you toss many times, you just keep track of the number. And that's usually what we do, right? And that's a very natural way to describe what we care, right? If something cannot be measured, also interesting study, but usually for application purpose, for business application is something we don't really care that much, right? And same as continuous random variable, even that would be the case where we would be concerned about ourselves more, right? Because continuous random variable, usually we have a measurement directly, and that's something we usually care about, right? Just like temperature, stock market indexes, that's the things. Okay, and for this topic, we divide in two parts. First part is discrete random variable. The second part is continuous. The reason why they divide in two is very natural, and from application perspective, discrete is something you face more often in the world when we talk about sampling. Okay, for many of you who are doing the accounting, I notice 80% of the class is from accounting. Then you will notice the sampling is very common, right? When you audit, you don't, when the audit process, right? You don't really go to the, you don't want to check everything, right? But you try to check some of them, right? You do sampling, okay? You do check something. And then you want to see how to do sampling, right? And how many to check, right? And that's commonly you would face. This is a standard problem for accountant, right? Or for auditor. And for continuous random variable, right? It's something for people who do finance. I notice the remaining 20% of the class is more from finance. So that part would be continuous random variable would be your concern. And in the later stage of this class, second half of this class, you will be a lot of the working on machinery is based on continuous random variable. Okay, so basically, almost second half of the class is based on some distribution of continuous random variable, and that will be the things that why we distinguish between the two topics and application. Okay. So let's get started. So discrete random variable, and again, why we want to distinguish the discrete and continuous because of tools. Okay, here the probability distribution function is rather simple because we have a finite number of outcomes, right? Or countable finite, right? We can count them and get basically each outcome would have a probability. Okay. And for continuous, that would be, you cannot list them because it's continuous. You cannot list in a table. So that means that all the things can be rather complicated. We need some integration or what, but don't worry, we probably don't work with integration, but we just, by proving something, we'll try to tell you how to prove it, but we really not entering into calculus. So the cumulative probability function will be the probability that x less than x. In the other word that we just add them up, right? Just like you add up all the probability because you can count them, okay? So that would be the key here, okay? So this example is rolling a die, right? And the probability function and the f, right? So hopefully there's no problem for this. I mean, but probably you will know whether you know it or not in the upcoming quiz on Thursday. Okay, you will know whether you're able to understand all this. And the next part is expectation and variance. So expectation is a weighted average, right? Just to recall, average is the simple average, right? It's add them all up and divided by n, right? That means each observation have equal weighted, and the weight is 1 over n, right? And the way why we do this is because every outcome usually we have same weights, right? But in terms of probability distribution, that would not be feasible because only if the simple case, each outcome is equally likely, right? But a lot of cases not, right? Say if you told the content a fair con is fine, but if you told say unfair con, right? Then it's not. It's very clear that it's not equally likely, right? And similarly, right? You just remember if you roll a die 2 times, right? And the sum of the 2 die will be a number either from 2, 3, 4, 5 up to 12, right? It's very clear that the 6 or 7 will be more likely than 2 or 12, right? So we cannot put equal weight on all the outcomes, okay? Then the expectation will be the x, okay, time what the probability of x. Okay, so this is expectation. The mean of is x and weighted by its probability, right? And the value of x is expectation, okay, and will be the difference from the mean and x squared, okay, the weighted by probability. Okay, so that's called the variance. Okay, it's exactly the very similar idea what we learned in the first class about the variance, but now it's not equally weighted, so it's not 1 over n. Okay, and there's no n minus 1 here. Okay, because not about sampling yet, but later you will see after this set of slide, the next slide, then you will see n minus 1 coming out again. Okay, and we know how to calculate this kind of expectation. I hope you know. And linear probability, this will be the linear property. Then we know when ax plus b, we can simplify it. The same idea here. And for variance, it's also the same idea here. Okay, I hope that would be okay. So this is useful. Those who study finance, that would be something you'll be working on. For more higher, the more difficult class, that would be something very common. Every time we calculate the variance, expectation, covariance. Yeah, talking about the Poisson. Yes, E is a constant. Yes. We talk about the Poisson soon. Yes. Is that okay? Because someone asked me the E is one number. That would be a the constant 2.713, something like that. 2.7, something like that. It's a constant number. We'll explain it a bit soon. Okay, don't worry about that. If you learn advanced math, then this is for DSC. I think that would be is covered. But don't worry, we'll talk about that. So there will be 5 distribution we cover, and we have covered the first 3. The goal of the day is to cover the remaining 2. But you will see all of them, or many of them, are related to, are interrelated. So this one, the more complicated version is binomial. And a special case is Poisson, and hypergeometric is a general case for binomial. Okay, so it's much more general. So a general case of binomial is hypergeometric. A special case of, so this is a special case. and you go to general case, you see general case, you got a hypergeometric. Okay, so that is the idea. Okay, this is when binomial, you just repeat, right? Okay, so that is how they're related. But later, when we talk application, then you will see why we need those. Okay, but just the goal of today is just try to cover these two different cases. So just a little bit repetition. Uniform is everything is equal likely, so it's 1 over n. Okay, and I hope there's no problem when you calculate the mean and the variance, which is coming from the first principle. We don't write mean and variance because it depends on what the value of x1 up to xn. So, but you're able to calculate mean and the variance, probability, all those kind of things. It's not something we didn't say it out, but if you check a textbook, they will calculate all kind of calculation, but you should be able to do it given your knowledge. And binomial distribution, right? Is again just to repeat because this is something to base on today, right? This is the foundation, right? So the sample space only have two outcomes, right? The sample space, right? The sample space S only have two things. Either you have success, you have fail, only two outcomes. And the probability of success is P. And probability of failure is 1 minus P, okay? And obviously, success and failure are mutually exclusive, okay? And even though we say only two outcomes, right? But remember, only two outcomes is the random variable, right? Actually, you can imagine in the complicated sample space, you have many, many outcomes, okay? Many outcomes. And you group all these outcomes to be success, group this outcome to be failure, okay? And the probability of this thing happen is P, probably 1 minus P, okay? So remember, they are the random variable, okay? So that's why it is covering actually much more general than we think, right? Even though you think there's only two outcomes, they're mutually exclusive and they're collective exhaustive, but actually it's a partition of the sample space, right? And indeed it's a lot of application, okay? And you can combine these two, right, to the following function, right? You can just with P to the X, 1 minus P to the 1 minus X, right? X is 0 or 1, right? And one stick, series cross, right? It's not success, okay? And there's a lot of application there, okay? And we have proof that it's easy proof. Actually, you should be able to solve this proof and make it something not complicated, right? But anyway, as I said, proof is not the goal, but you should definitely able to solve this, right? Why the expectation is P, the variance is P times 1 minus P. That's something shouldn't be difficult for you. I mean, at least I hope you should be able to understand how this is being proved, right? And I'm not going to go to the graph, but you can easily see the proof is being done. I hope that's not something terribly complicated, okay? And let's go to the binomial distribution, right? Binomial is asking to repeat the binomial trial n times independently, okay? So you just keep doing this, okay? And n times, so that's why you have n plus 1 outcome, because you can have all fail and all success, and you can have this all failure, all success, 1 success, right? So there's n plus 1 outcome. And you want P X success, n minus P fail, right? And And there's a different way to reorganize this. Those are NCX. Okay, so this definition. Okay. So there's something that you should know. Okay, and this is the mean, right, and the variance, right? We spend quite a few time to prove it, right? Y is NP, and NP times 1 minus P, right? But as we hint before, right, this is special case a binomial under NP, right, is x1 up to xn, the n of them, and each one is a binomial P, right? Because each one is numbers are set together, right? So that's each one is binomial, right? That's why expectation of x, right, is expected x1 up to xn, right? And each one is p, so it's p plus p, so it's np. Okay, so that is how to prove this, and same as a variance, right? So that's how you arrive these two formula. Okay, of course we have shown you how to prove it from the first principle, right? But you don't have to prove in this way, but this is the more simple way. Okay, just to remind you that for the quiz, you expect to know this kind of, solve this kind of question, right? Although I didn't tell you this is the binomial, you should able to see the application is actually binomial. Okay, this should be because you are randomly pick out 5 and you know the P probability of a consumer like spicy food is 30%, 2 of them is good, then you should be able to figure that out. Okay, something that you should be able to handle. I mean, this is something that is able to see which probability distribution to apply into which case. Okay, so that is the, and you auto compute all the probability. Okay, so that is the goal. Is that okay? Any question? I think we just review everything we covered so far. Send a question. If okay, can I have you all say okay? Because we will be doing a Poisson immediately, the new thing. So feel free to ask questions if anything new, but otherwise we will be working. Okay, good. No, it's open book. I think we should be open book, I guess. At least for the quiz. The test, I don't know, because we might be resuming face-to-face, so I haven't figured out what to do with our quiz yet. But I will be, I think. But I guess if any formula, probably I will. Yeah, let's figure out that out. Either I give you or you can. If the quiz is online, then probably I cannot make you memorize, right? So, well, there's no need to, I mean, binomial is the case. Oh, someone asked me, how do I distinguish between binomial and binomial, right? Binomial is the case. So binomial N and P, right? General case, but binomial 1P is exactly binomial P, okay? And if I ask, suppose I just pick up one randomly chosen customer, what's the probability that he likes the food? Then it's binomial. But you pick up 2 or 3 out of 3 two of them is or not, then it's binomial. Okay, just the building up. And of course, in the real application, you just focus on binomial, right? Because binomial cover the binomial already. They're the same because it's a special case. Because binomial is a special case of binomial. So in terms of application, you just remember binomial is fine because binomial already covered binomial. Does it make sense? So you don't really need to distinguish them because binomial already cover it. So basically, when you apply, it's just like when you try to sample things n times, each time independent, binomial apply. That's it. That's when you remember in your head. So there's nothing more than the thing we described in this. Actually, no more than we put in the slide. Is that clear? So feel free to ask questions if you want to. Okay. If no, then we go to Poisson, and you will see that Poisson is a special case of binomial. Okay. So how do you get this one? Did I make a mistake? So let's do it together. People ask me, maybe I compute wrongly. So 5C2 is 5 factorial, 2 factorial, 3 factorial. Okay. So just calculate by hand will be 5 times 4 and 2 times 1, right? 2, so this is 10, okay? And so this is 0.3, then will be 0.09, right? And okay, this is 10. So, and let's see, 0.7 to the power 3, 0.7 times 0.7 times 0.7, right, is 0.343, okay? So let's multiply them all together, times 0.09 times 10. Oh, yeah. So, yeah, that's right. It should be 0.3087. Yeah. Sorry. I guess you are very good. This binomial should be very good. So those of you who actually calculate and should notice there might be a mistake. So this would be the right answer, but the formula is correct. So any further question? Very good that thank you, Yankin. That was very nice of you. Is that okay? Any more questions? Yeah, I'm sorry for the typo. I guess I changed the question somewhere and then I forgot to change the answer. Any more questions? Okay. If no, then we go to Poisson. Any more question? Anyway, but you will know you have question when you do the quiz on Thursday, because it's a good way to let you know whether you know it or not. Okay. Next slide, we prove it. There's nothing more to show here. So what we are working on today now is first a special case of Poisson. So special binomial, which is called Poisson. Poisson is a guy, right? It's a person, a mathematician or a statistician who discovered this, okay? So that's why it's named after him. So it's a very interesting name, Poisson. I think it's a French guy. But anyway, but what it is, okay? So imagine you have a binomial, okay? As I said, this is supposed. What typo? Poisson. Did I make a mistake? Poisson. Oh, well, yeah. Oh, yes, Poisson. Should be P-O. Yeah, I always cannot spell. Yeah, P-O-I. Yeah. Oh, someone told me that this is Poisson, should be P-O. Poisson. It's P-O-I. Sorry, the type should be P-O-I. Poisson. Okay, it's Poisson. Sorry, correct. Okay, thank you. So Poisson. So binomial trial. So binomial distribution is you have n objects, right? It's 1, 2, n trial, right? And each trial can be success or failure, right? Each time. Okay. And with success probably P, right? Failure minus P. Okay. And the major question here is, okay, if this n is very large, okay, and P is closely small, okay, but NP is still something between 0 and infinity, okay, say multiply is still okay. And in that case, okay, can we simplify our calculation, right? Remember, this is the P x 1 minus P m minus x. Is there any way to simplify this? Okay. Turn out to be the simplification this one. Okay. And why we need to care about this? Okay, why to care about all this thing? Okay. This is what we call rare event. Okay. And what are the rare events that you would care? Consider the case where you have some, say, customer arrival. Okay. It's a very common application, right? For business, that's usually you care a lot. Or number of defects, okay? Customer arrive, you can consider each, say, over the morning, right? Suppose during the morning time, say 9 a.m. to say 12 a.m. 12 p.m. Sorry, 12 p.m. right? Or 12 noon to make sure there's it's a morning thing, right? And they're 3 hours, right? But you can cut them into very small minutes or even second, right? Or even millisecond, okay? And in that case, right, what's probability that a particular customer arrive at a particular point of time, right? The probability of that will be very small because when you cut smaller and smaller, this probability appear in particular thing is very small, right? So then you can ask how likely that the consumer would comes in, right? And in that case, a Poisson would be a good model to model this. Okay, it's number of consumer arrive, or how likely a DVET has been working, say how many mainly is usually for consumer arrival, or how many defect you have each day, or how many people would have sick, and so on and so forth. Okay, it's a rare event. Okay, Rare means doesn't mean it's completely unrelated, it's completely improbable. But just like when you have the time horizon long enough, then things become rare, right? Because when you cut the time into very fine minutes a second, then it's very likely that, I mean, it's very unlikely that for that second to have some event happening. Okay? So that becomes rare. So that means you try to model certain number of outcomes would happen. And the only assumption that we are making, or the main assumption we are making, is whether someone coming here is independent of someone coming here. Okay? Even though a lot of people coming here doesn't affect people coming there. Sometimes it's okay, sometimes not. But sometimes this assumption we have here. And say, suppose people model stock market, some earlier model would assume people would arrive in a Poisson manner. Okay, maybe people come in the morning, people come in the afternoon. Okay, and that this kind of process can explain why you have bid-R spread, but that would be other model we need to model. But that is modeling arrival of certain thing. If the arrival is independent, Poisson is a good application of those. Then I'll justify why this is what it is, okay? And turn out to be this NCX, okay? PX 1 minus P, okay? So what's lambda here? Lambda here is NP, okay? And turn out to be will be E raised to the power negative NP, okay? And this E, we will tell you what it is, but just a constant, okay? So it's 2. Somewhat related to 2.7, okay? We will explain what it is, but if you, the Taylor series of expansion, which will tell you this is E to the power X, will be X over 1 factorial, X squared over 2 factorial, X 3 over 3 factorial, and so on and so forth. Okay, if you put X equal to 1, then your calculator will give you 2.71, blah, 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 blah. And this we call E is the natural number. And you may ask what the natural number is, because it's so natural, it appears in a lot of math calculation. So that's why it's a natural number. It's more natural than 1, 2, 3, 4, 5 indeed. So that's why I call natural number. But this is what this means. I hope I answered some of the questions people asked at the beginning. Okay. So turn out to be this Poisson has a very interesting feature. The mean equal to the variance. So both of them are lambda. Okay, of course we'll prove this is right. But this should be noted that this is different from the binomial, right? Because binomial we have expected X is NP and variance of X is NP1 minus P, okay? And as we said, P goes to 0, so that's why this will be similar to NP, okay? That's why these are similar. That's the main reason why we have the same mean and variance when under the condition we discussed. Is that clear? Any question? Okay. If no, then we are going to talk about the application. Before we the graph first. So as we said, that will be similar to binomial, right? So that is lambda equal 2 is very similar to This, when lambda bigger, then it will more similar to binomial. Okay, but remember, Poisson can be very, very big number, right? So it must be skewed to the right because it can still have value when you have x is very large, right? Binomial, you have something is not there, but when because binomial up to n, right? But here is n go to infinity already. Okay, just lambda, remember is NP. Okay, number binomial. But anyway, let's figure example. Okay, there's something that usually we make the assumption, right? Number of customer in a restaurant for each hour follow a Poisson distribution with mean 5. Okay, and what is the probability that exactly 2 customers arrive in the next hour? Okay, and so here is a Poisson, so Poisson is mean 5. Okay, so which means that lambda is 5. Okay, so the question exactly 2. So that is very simple, right? So it's just basically e to the negative lambda x factorial, and you just apply, then you should get the number. Okay, and you can easily find out, instead of asking you exactly, okay, if I ask you what is at most, okay, you should be able to show probably x less than 2 with probability x equal to 2 plus probably x equal to 1 and plus probably x equal to 0. Okay, so this is something called lambda. Yes, lambda. This is called lambda. Yes, lambda. Yes. So you should be able to figure out this by yourself. And also there's a usually something like the following should also hold. I mean, there's a usually assumption is every hour Poisson is mean 5. Okay, and that means if every 2 hours, right, can be has a Poisson lambda 10. Does it make sense? Okay. So if I ask what's probability that exactly 2 in the next 2 hours, then you will calculate the same, but the mean will be 10. Okay, I hope that would be something not typical to see. Is that okay? Good. So we'll quickly go over the proof and then we'll have a break. Okay. So maybe just only this proof and then a break. Otherwise, maybe you will wait too long. Just this one a break. Okay. Because this one is rather quick. So expectation of x is x times p of x. Okay. And p of x, the probability will be given by this. Okay. This is something is given to you. You know it already. So now the next thing is x from 0, so you can start from 1 because 0 times anything is 1. Okay. The second thing is here is e exponential e is constant 2.713 to the negative lambda. This is unwritten x, so you can take it out. So that's why I see it. And the third thing is x times x factorial will be equal to x times x minus 1 factorial. This x cancel out. So that's why this, you have this guy. Okay. And the next step will be x to the power x, okay? X start from 1, okay? There at least one item here, so that's why I can take one lambda out. Okay, it becomes x minus 1. No, the quiz will be the beginning of next class. So for those who arrive late, don't worry. Next class, we will have a quiz, not this class. First day. We just cover up to the Poisson. We just cover in Poisson the mean, and then we'll have a break. In case you're coming late, then you can just check the video again, and if you to cover up things that you miss. And you start from 1, okay? We use the same trick here. Then y can start from 0 because x is counting 1, 2, to infinity, right? And I said, let's count from 0, 1, can also from infinity. Okay, that means x minus 1 is equal to y. Okay, so x minus 1 map to y, x minus 1 map to y. Okay, and this will require here, the next step will require some result from math class, okay, which you're not expected to know, but just show you the formula, but we're doing already is 1 plus x over 1 factorial plus x squared, and so on and so forth, right? And this guy is summation x is the same notation here. Y to infinity to y. Okay. So this is something that if you try to check Wikipedia or other place in the math textbook, this is something given. And if you put x equal to 1, right, e to this, sorry. Right, so you actually can see this is 2 already. This is 0.5 and so on and so forth, right? Then you will see how, sorry. So this is 1, 1.5, 0.3, right? Sorry, this is not 0.3. This 3 factorial is 1. Is 0.1, 0.17, and so on and so forth. 4 factorial, then it's getting smaller and smaller. So how can I change x from 0 and to 1? Because 0 times this guy is 0. So it doesn't really matter, it can come from 1. So put it this way. X and times certain thing, maybe a star, okay? Okay, would be equal to x from 1, x star. Doesn't really matter because 0 times certain thing that is well defined, then you can start from 1. No, when you but yeah, when you're 0, you cancel, doesn't really matter. When you cut this out, then you cancel out. You're asking we cancel out first. Why? The reason is when it's 0, we can't cancel out the cases. When it's 0, we cannot cancel out because 0 when x is 0 and the 0 factorial, but 0 factorial is 1, so 0 cannot cancel out 1. So when you cancel out, say a over b, right? The formula is right. You can only equate to this, right? Only an a and b are not 0, right? At least b is not 0. So, and now this guy is e to the lambda just by the definition, okay? And lambda, negative lambda cancel out, just 1. Okay, so that's lambda. Okay, so that's why we prove this lambda. Of course, turn out this is NP, right? This is the mean is NP. So there's nothing, if we divide NP as the lambda, so that's why we didn't prove anything, but that is what it is. Okay, we should have a break of 15 minutes and we come back. So we come back at 11:35. So break until then. So feel free to ask any question or we will break. Why this expectation for the previous question? So maybe I should, let's see. Previous question, you mean this one? Oh, I said is every hour, the mean is 5, then every 2 hours is 10, the mean is 10, is it? Do you think it's fine? Yeah, that's what I mean. If every 3 hours, 15. No, because they're independent, just some of them say, is that clear? I hope that's okay. Someone asked me, is the exam similar to the quiz? Well, the test will be more difficult. Depends. It depends if how well you're doing the quiz. If the quiz is already difficult, then of course the test will not be more difficult. If I think the quiz is too easy, then it will be. I don't know. I answer your question, Yanso. I think the quiz will be a little bit easier than usual. I mean, that would be because I want to check whether you know, but it will be more related to the. It'll be a little bit more difficult. Yeah, I hope that would be. I think the text would be exam would be very similar to what you see in the textbook. Some question there, but of course would be similar style, similar difficulty level. The answer question, Yang Sok? So someone asked me why Poisson represent rare event. Okay, so actually we'll do it after the break, but the main idea here is Poisson is indeed similar to is a binomial approximation when n go to infinity and p is very small, right? So that means it's a rare, because it's a rare event, because you can imagine over the long period of time, right? And you divide the period of time into very small interval, small fine interval, right? And this small interval, right? And you consider a trial, right? But it's a binomial trial, right? And the p is very small, right? Because cut is very small. So that's why it represents a rare event, because it's because we know the Poisson is a special case of binomial when n is very big, p is very large. So n is very big and p is very small. And p is very small is a rare event, right? Because it's, does it make sense? Cai Kwa? What is p? Next page. Oh, okay. So how we relate NP here, okay? So you can imagine an hour, okay? 1 hour, okay? It's divided into, say, 5-minute interval, right? Each minute, 5 minutes. Okay? So in that case, in that case, we have 1 hour, you have n equal to what? 12, right? And what's p here? Okay, so the mean of this is 5, right? So which means that p will be 5 over 12 if you try to convert that in that way. If n is another number, say n is, consider n is 60, okay, consider minute, right? 1 minute, 1 interval, right? What's p here? Will be 5 over 60, which is 1 over 12. Is that clear? Check out. Yes, is for each interval, how likely is success or failure? That's P, right? This is a binomial is a success or failure. Yes. And we assume some assumption is only one would arrive no more than one. It's just it's a binomial, right? Because it's binomial trial, right? It's like whether you have one arrive or no arrive. This is P. This one minus P. Does it make sense to you? You can still ask me if you have a question. Weigh in as I think as the homework, whether do we need to calculate everything, mean, median, skewness. The answer is you just pick up whatever you think is appropriate. You don't have to cover everything. Yeah, because sometimes, say for example, the income, right? The income case you don't is so skewed, right? That probably median is meaningful, right? So it depends. But of course, the skewness is trying to support the idea you took the median rather than mean, right? And somewhat like that. But anyway, it's up to you what is the application. So that's why you have to decide what to do. Okay? Very good. So I guess now I would want to talk about the second moment. Okay, so let's resume the class. So let's talk about the variance of the Poisson. Okay, variance of Poisson. If you remember how to prove variance, so variance of x is using the second moment, okay, minus square of the mean. Okay, this below is lambda square. So this is something we want to know. Okay, and with the trick of this trick, okay, expected x squared is equal to expected x squared minus x plus x. Okay, the reason why is this guy, which is this guy, right, will be easy to calculate rather than calculate this directly. Okay, so that's why we use a little bit detour. Okay, we calculate this guy first, and plus lambda, we get the x squared, and then we can calculate the variance. Okay, the proof will be not difficult. You will see the same trick. We'll use the same trick. So expected x times x minus 1, okay, just the variable x times y1 and times p of x, okay, and p of x will be by this definition, okay, and since x equal to 0 and 1, so you just start from 2, okay, because, and then you can take this out, okay, because start from 2, you can take this out too, you get just minus 2, okay, And because you have x and x minus 1, so you can just take this x and x minus 1 is x minus 2. Okay. And then you can see the same trick applies because this guy add up to 1. Okay. If you write y equal to x minus 2, and then we write everything y, and then you can see will be equal to, be equal to e to the power lambda. Okay. And this, they cancel out. So that's why lambda square. So the same trick here, it just, okay. So that's why this guy is lambda square plus lambda. Is it okay? Any question? Okay. Because the same trick, I guess this will be, looks familiar already. Let me finally solve because we already actually have that, right? So this guy is proven to be this one, right? And this is lambda square and cancel out this lambda, okay? Okay, that's a proof for the variance, okay? Finally, I want to show something that is not in your slide, but just to quickly give you some informal idea why Poisson, that is a Poisson, okay? Just a very technical thing, so that's why I didn't put in the slide. So consider X is a binomial NP, okay? How you relate this ratio, probably X and X plus 1, okay? The denominator will be this guy, right? Just definition. So numerator of this guy, okay? And the denominator has one more P, so that's why P is here. Okay, so let's compare this. One more P. Okay. And you compare the numerator, okay, and denominator for 1 minus P, and you see the minus 1, so there's one more 1 minus P here. Okay. And the final complication comes in this guy, right? And this is NC x plus 1 be equal to n factorial x plus 1 factorial n minus x minus 1 factorial, okay? And NCX, right, is n factorial x factorial n minus x factorial, okay? And same n factorial, okay? And x plus 1 can be written x plus 1 times x factorial, right? So that's why this is gone, okay? The same idea will solve this, and this is gone. So that's left is n minus x and x plus 1. Okay? And as we said, now we consider case n is very big, okay? And p is small, okay? That means that n minus x is close to n, right? So that's why this you will write n. And p is very small. That means 1 minus p is close to 1. So that's why it's gone, right? And we declare NP is with the denote, right? We write NP is lambda, okay? NP, but no different from lambda. Just let it, okay? So that means in the next line, you will see we will save this formula. Lambda plus x plus 1 is p of x, okay? So we will have this, the formula to be used in the next line, okay? So that's in a binomial how x with x plus 1, in particular, n is very large and p is very small. So this is the formula. Okay. Under this, we will show you why Poisson formula look like that. Okay. So very quickly. Okay. So that's the case. Okay. Now, actually, that means written in a better formula, P of x is lambda over x, P of x minus 1. Right? So actually it's here. Again, you can rewrite this as P of x minus 1 is lambda x minus 1 P of x minus 2. Okay, so that's why your lambda square x minus 1. Okay, and you could repeat and repeat and repeat until you get to P of 0, which gives you lambda x because we repeat 1, 2, up to x time. And this is x factorial. Okay, so remember this formula. Now you have sum of all the possible values 1, right? And P of x is this guy. Okay, just put that in. Okay, and do note that P of 0 is something unchanged, unrelated to x, right? So you can take it out. And the whole summation can be written in the bottom, right? And as we have seen, this guy is e to the power lambda, okay? And inverse is negative, okay? So you put this back into here. So that's why it's explained binomial is e negative lambda, lambda x factorial, when n is very large and p is very small. Okay, and that means it's a rare event because it's very small p. Is that okay? I hope that gives you some idea why this is true. And as I said, this is not the part of the proof I want you to remember. So that's why I didn't put a slide, but just give you some hint why this is, when this is the case, this is true. I'll answer some of the questions you have in your mind. Is that okay? Any question? If okay, can you type okay into the chat? Yes. Now we are done. Thank you. So we're done with Poisson. I hope it's okay for you to understand. Remember, Poisson is just nothing but a special case of binomial. When n is very big and p is very small. I think I repeat this statement a lot, but I hope that will convey into your mind. So the next part would be another very similar to Poisson, related somewhat in another manner. Rather than go to infinity, but we just in the finite, still n is very small. Okay, n is not big. Okay, and this is more generalization of Poisson rather than a special case. It's a more general case. Okay, and I notice many of you are from accounting major, and this will be very interesting to you a lot of time. The question would be, for Poisson, for binomial, it's just like the n trial, right? Each trial is independent, right? But in some point of time, you are not doing independent thing a lot of time, right? When you do auditing, right? Suppose you go to a warehouse, right? And maybe a warehouse that is something easily deteriorate or something that have some defective product, right? Or the machine, right? And you are trying to say there's a n object here, okay? And A of them are bad thing, okay? Or bad thing. Or good, depending on what you want, or good, doesn't really matter, okay? Depend on the choice of n objects, that's the n object, okay? There's A object is good, right? And very often we are trying to have a sample of size n, okay? We draw an n over there, sample, n sample, okay? We're asking what's probably x of them belongs to A. Okay, all of them are good, say. Good, if we consider good, okay? Or bad, right? Why do we need that, right? Because we go there and want to check the inventory, right? Whether the inventory has fake or not fake, right? Maybe 99% are the right thing, right? We don't really care, right? Suppose you go to audit, right? The guy said, oh, I have so many inventory, right? You want to check what are there inside the box. You don't know whether it's empty box or there's a thing, right? And then you want to try to pick up some box out and check, right? But you take all the box out and check, right? So you don't put it back, okay? There's a sampling without replacement, okay? You take all out. The first item you take out, right, is different from the second item you take out, because you take out, you don't put it back, right? And in that case, we require a hypergeometric distribution, okay? If you, every time you take it out, you put it back, then it's a binomial, right? Because every time you take out, you put it back, right? In that case, P will be equal just to A over N, right? What's the probability you draw an item that's good, it's A over N, right? And you put it back, every time it's A over N, right? And if you put it back, it depends on what you draw, right? Because suppose you just draw two items, right? Then the property of the first item that is the thing you want is over N, right? The second one depends on whether you have drawn this thing, right? If first time you drawn, then you don't put it back, no longer A, right? Suppose you drawn, then if N minus 1, then you have A minus 1, right? If you drawn it, right? But if you don't, you become N minus 1A, right? It really depends on whether the sample space become here or become here, depend whether you draw it, right? Okay, so that's why it's rather complicated thing, okay? And here you can see if N is very big, okay? N is very big. If the big N is big, okay, then we will go to binomial. Okay. Later we don't prove this fact, but actually you can see this is right, okay? So let's, this item, okay, number of items. So here just go to formal definition. So hypergeometric distribution, and there n objects over here, there's n object, okay? A of them we consider success or good, and there's n minus A we don't call success or good, okay? And the question here is, we try to randomly draw n object here, okay? And do note that's different from previously. Now, once we draw an object, okay, we don't put it back. So once we draw, it become here or here, okay? And we draw again, it can another thing, right? So you can see very complicated process is going on here, right? Binomial, you always draw this thing repeatedly, right? But hypergeometric is more, I would say, more realistic, right? Once you draw, then things become different, okay? So here we ask, okay, this write down here is, suppose I have sample of total number of the sample space is n, right? The population is n, okay? A of them, all of the A of them are something we care. Now we have a sample N item without replacement. What is the probability X of them belong to these A objects? Is that clear what we are doing? Is that clear? Can you type OK? Because this is very important. Okay. So now, first is the probability, right? The denominator is how many types of style can be done, okay? And we are drawing n objects, right? So that's why it's n, big N, C, small n. I hope that's okay, okay? The difficulty comes from the numerator, okay? And, big N is everything in the warehouse, okay? This is a population, is the thing that we try to draw things on. And you know, out of the big N, A of them is something we think we care. N minus A, we don't care. And then we're trying to do a sample of size N. And that is small n. June? Okay, we're drawing the sample N, so N sample, okay, without replacement. So each time you draw N, one is to draw object and draw, and okay, once you draw the first object, you want to see whether it's belong to A or not belong to A item. The second one, you want to draw again. Okay, I draw N object. You ask X of them is belong to the successful object A. Okay, and this A is how likely you get a successful one, right? This is success. This is failure. I mean, if you call A success or good or bad, right? Out of A of them, okay, you draw X of them, okay? Here you have N minus A is the failure object. You draw N minus X of them, okay? So that is the idea, okay? You don't have P here, but you're assuming every draw is equally likely, okay? But of course, if you have different probability, then you would multiply probability differently. But just focus on the simplest case where each object is going to be drawn equally likely. Okay, there's low loss of generality because you can just make more object, vary the number of objects, so make sure that to achieve what you want. Okay, and as we said, this is a quality control, right? You try to draw. I go to warehouse, right? A of them is something you want to check, right? You want to take out an object, what's the probability? Okay. And the mean, actually this mean is very close to NP, actually it's NP, right? If you just draw once, okay? Binomial, it means keep drawing this, right? Binomial will have P equal to A over N, right? The binomial, okay? A over N, right? So this is NP, okay? And here we have NP, this is 1 minus P, right? And here we have another interesting term that is different from the binomial, okay? Here, when you see N go to infinity, right? This thing go to 1, okay? So that's why originally I said when we have a very big population, okay, very big thing we try to look at, then same as binomial. Okay, we didn't prove it, but you can see from the variance, this is the case. Okay, we'll prove this is true, but this is the two formula we have here. Now, A is the object that we think that is we care. So N is total number of objects. A of them is something we think that is success. N minus A is not success. So just repeat a little bit. Public notation is so N is the total thing in the thing you want to look at. Okay, and A of them we call tick, and M minus A we call not okay, right? That means if you keep drawing this sample in the binomial case, A over N is P, right? And NA over N is 1 minus P, okay? And is that clear? And the thing is, you draw N sample over here, okay? And the thing is different from binomial. Binomial hints, I keep drawing this is the background the same. But in this case, once you draw one thing out of here, the sample is reduced to N minus 1, okay? In addition to that, depends on what you draw, right? This A minus 1, this is still N minus A, right? But what's left here is N minus A minus 1, depends on what you draw, okay? So that's why there is the key difference between the two. Is that clear? And for those of you who do accounting and audit, that would be, they see the next example, then you will easily see why we need that. But just save me, just wait one more slide, then you will see the application. Okay, I hope that is fine for the moment. So let's, yeah, there's a question? Yes. So please ask. If no, then I just very quickly go over the graph, okay? Here, as I said, A over N is P, corresponding binomial, okay? If binomial, that is something, NP is, P actually is half, right? NP is 2, so that's a say, your binomial 2 is something like this, okay? That looks very similar, okay? And similarly, this is another case, right? Which is very similar to binomial, okay? So, but anyway, let's give you an example, then you appreciate what we're doing here. So, in a warehouse, okay, 30 computers, 4 of them are defective, okay? And here, N is 30, okay? A is 4. If we call defective is something we care. So now we have asking probably 2 of them are defective out of sample 6. So we are saying that sample is 6 and defective, we want X is 2. Is that clear what we're doing here? Good. So just before I go to proof, I try to explain why we need all this kind of, we learn all this kind of thing, right? Because you may ask, how to distinguish binomial hypergeometric. Here we are taking the sample out of 6, right? That we are not doing, we take the sample, we are not replacing it, right? So that without replacement, then it's hypergeometric. Unless it's clear it's replacing, each run is the same, then it's binomial. But it's clear that you take 6 sample, right? You are not taking one sample and put it back. If you put it back, then it's binomial. Quan is it? Yeah, good. So then just put the formula. I'm not going to do this part. You can check whether I do it correctly or not. If not, let me know. Maybe I typo or not, but you can check. But I want to you to pay attention why we all do this. Actually, the same you want to know is here is we have some idea of what's going on here, right? We have no this n, this a, we're asking x, right? Given n, right? Basically, we are trying to have a population, right? Which we have n and a idea, right? And later we call a sample, we do some sampling, right? Of n, and we want to calculate probability of x, right? So this is the idea, okay? And the thing is, we want to know the probability of x, right? Given all this n, and a, right? And or same for binomial, but just use Poisson, sorry, this hypergeometric example. And usually the real question is the opposite side, right? We have a sample, we have a particular x happening, right? We want to know actually to try to, we know n, usually that's not a problem. The problem is a, we try to guess what it is, right? And we may have some idea what the probability A is, right? Some pyra, right? We can use the base updating rule, depend on what we observe, to try to let us know what A is, okay? So that is the main application of what we are doing. But we don't go over that, but you should be knowing that one of the main applications we learn is like this. But of course, that would probably be beyond what we learn, but that would be the, but you should know it when you, if you go to other more advanced class, they will, this is one of the application, okay? But you should know it from, you know it now, because although we are not explicitly asking you to know it, but you should combine these two ideas, that would be, they will be there, right? Because there's something you want to know, right? As an accountant or auditor, you want to know A, right? Then what you do is you have some prior information about A, and you try to do a sample, and then you try to update yourself what is the knowledge about A, you through the base rule, okay? Or later we learn hypothesis testing in the second half of the class. We also do something similar, okay? We do something much more easier, but the base rule also can be done, but we're not going to detail on those. I mean, but you should able to figure that out. Any question? If no, we go to proof, and then that's end of the class. Okay, I see no question here, so let's go to proof. The proof is not complicated, just a little bit tedious, but you will notice the same proof concept appear again and again, okay? Expected x, okay, is x times probability x, okay, P of x, okay? And here we use the same trick here. Ax is equal to A over x, A minus 1, x minus 1, just like taking a thing out. Why this is true? Just basic, we just elementary proof is A factorial, x factorial, A minus x factorial is equal to A times A minus 1 factorial, x times x minus 1 factorial is A minus 1 minus x minus 1 factorial. This is A over x, A minus 1, C1. So this guy is this guy. Okay. So do look first, x from 0 doesn't really mean anything, so you can start from 1. Okay. And using this idea, you can take out and minus 1. Okay. And here I minus 1 and x cancel out, so that's left A. Okay. Now the next step is this all take out. Okay. And you can see the goal is here. Okay. That actually means, actually we expect this guy is 1. Okay. And it's not difficult to see this as 1 because this is a you can change x into y, okay? Everything minus 1, okay? And become 1, and then x minus 1 become y, okay? Okay. Then this is indeed a hypergeometric distribution with parameter n minus 1, n minus 1, a minus 1. So sum of all this is 1, okay? So this y is n times a over n. So remember this is just np, right? Because p is just a over n. Okay. Is there any question? So a little bit quick here because I think that is a very standard we have done many times, but just wait. If okay, then please type okay. Otherwise, I would go over. Otherwise, you want to explain? Is there any particular part you want to explain? Oh, why those swing to 1? Because this is you can check this is, you think a prime is a minus 1, okay? And this is kind of a prime y, right? And n tilde is n minus 1, will be n tilde minus a tilde. Oh, okay. And this is n minus y. The denominator will be n tilde n, right? N tilde. Okay. In that case, this is actually a hypergeometric distribution. You add from 0 to n plus 1, to add them because summation of all probability should be 1, right? Yum sum, yu sum. Oh, of course. If you don't like this, you can always do the trick is actually compute it is always 1. Okay, but that's a trick why it's 1. I understand if you've seen the first time, you wonder why this is 1, but it's actually the shortcut is always 1. Okay, and the next, again, we will do the same trick. You will see it's very quickly, you can prove it. So again, we don't prove second moment directly, right? We prove this guy because it's this, right? We know this is NA over N. We want to try to show this one. Okay. And again, this same, this is probability X. Okay. And starting from 0, 0, starting from 1 is also 0, so start from 2. Okay. And here I use the same trick. And n is n minus 1 over, sorry, it's n over n, n minus 1, n minus 1. And the same trick apply again, n minus 1, n minus 1, and nc2, n minus 2 over small n minus 2. Okay? So that is how you get this guy, the denominator. Okay. And the numerator, you do the same trick twice, right? So you have ax will be a over x, a minus 1, x minus 1, and a minus 2, x minus 2, c. Okay, just take out twice, you just subtract twice, and this one cancel out. So that's why you have a minus 1. Okay, and now what we do is these things are unrelated to x. So that's why you can put this in the numerator, right? And denominator is here, okay? And again, this guy, okay, use the same trick, this is 1. The reason is this is again, a negative binomial. You can just see is n minus 2, a minus 2, n minus 2, okay? You can see this is the same thing, just 2 less of everything, okay? And that you prove this guy, okay? Once you prove this guy, now we're happily we can prove the variance, okay? We prove this is NA over N squared. And from the previous slide, we have this plus that, okay? So here comes a little bit math here, is NA over N, okay? Take out 1 is here, square, so you just left 1 item here. Take out is N minus 1, A, okay? Now, how this part of this part is use your elementary school technique. Fraction add together, you need to find a common denominator, right? Which is n minus 1 over n, right? So here you times n, so this times n you see here, right? And here you have you make a common denominator. This guy, right, is n minus na, right? So times n minus 1. Okay. And then how you end up in here, okay? What you can do is just to nothing, but just expand. Okay. I think from now you are the, okay, you can just multiply out, okay? And with expand, you will see this. Okay, I don't think I need to show you why this is the case, but you can simplify. You should be able to see n squared minus na minus n and plus na. Okay, you should be able to check this is the case. Okay, and then you can go up to here by factoring. Okay, you see n squared. You can see n and it's cancel out, right? So I think you can easily check this one, okay? So the only thing I want to say at the final is this guy, right, is less than 1, okay? So that means that the variance of a hypergeometric has less variability than the binomial, okay? This is not surprising because you keep drawing a smaller and smaller sample, that means the variability should be less, right? Because the binomial, you just keep replacing. So every time you draw, then it's replenish. But this one, you draw and draw. Once you draw to the very last, then you don't have much variation, right? So it's so that's why it's less surprising at the end. Okay. I guess that should be done with the proof. I guess I don't have anything more to say. Continuous variable, we cover it. Next class we will talk about, we'll do the quiz first, and then we'll talk about this continuous random variable. Okay. If there's no question, then I will stay here for question, but I will say bye-bye. And then I will remain here to answer any question you might have. So feel free to ask a question, but just remember to make some revision before you go. Well, you say upload the Excel document with the assignment. Yeah. The source data is just like the data is from download from where, or you collect by yourself. That's the source of data, what I mean. Is that clear? Because someone asked me the assignment, the source of data. You just say the data is from where. Is that clear? Yeah. If you collect by yourself, then just like this hand collect the author, yeah, that's fine. Just a way standard way, just try to check everything. The newspaper, that's the standard way. It's not something I ask additionally from what you do, but just very standard thing. You can just go to see the newspaper. That's something very normal. So any further question? Let me know. Okay, if